Okay, so good morning, everyone. I'll be talking about just do my slideshow there. I'm going to be talking about enthalpy today. So this is a very short module. I just want to stress some important points regarding enthalpy. Also to differentiate two reactions later on that will be very useful for your lab experiments or your lab reports. And then also as requested, I'll be doing one example. I'm going to do a worked example for enthalpy wherein it involves phase changes. So let's start with the definition. So as defined, enthalpy is a thermodynamic property of a system. It is the sum of the internal energy added to the product of the pressure and volume of the system. It reflects the capacity to do non-mechanical work and the capacity to release heat. So you see a lot of terms here for this equation or for this definition. So just get my pen tool. So let's talk about the different terms. First, a thermodynamic. We need to say thermodynamic. Again, thermal. When you hear thermal, it's temperature. And of course, we are very specific with heat relationships or heat changes or heat properties of a system. So enthalpy is again an important concept that we might uh, be encountering in the future. So it is the sum of the internal energy added to the product of the pressure and volume of the system. I have a separate PowerPoint for this, wherein I get the derivation of this formula, wherein it talks about constant pressure and constant volume conditions. So, but for now, I won't be using or doing that derivation. I just want you to get or capture the important concepts regarding enthalpy. So it also reflects the capacity to do non-mechanical work and the capacity to release heat. So later on, if you've uh, encountered the derivation in another video, you eventually know that here H actually just becomes Q, or delta H is actually just Q. Okay, these are the enthalpy equations that I'll be working on in this presentation. Okay, but before we go to that problem solving part, uh, this is what I was trying to stress. I gave you handouts for enthalpy and calorimetry, but it did not really focus on enthalpy in this definition. Okay, let me just move me. Let's move me. Okay, so that you can see the full definition. It says here enthalpy of change occurs in the change of phase or state of substances. For example, if a solid is changed to liquid and vice versa, of course, it follows that enthalpy is changed. So converting solid to liquid is uses a specific heat, which is the heat of fusion. And when liquid is converted to steam or gaseous form, that's heat of vaporization. This is very different from the specific heat. I'm sorry, what was that? I think I pointed to something. Okay, this is very different from the specific heat that we were talking about in the calorimetry or the thermochemistry modules. This is, of course, specific heat, you know very well. Let's see. When we talk about specific heat, it is more of the internal energy of the object or the system, wherein it doesn't change phase from one phase to another. It's internal. It's the movement of the atoms in the system, but not really to phase change. When there's a phase change involved, we talk about enthalpy. But of course, they are still very much related to your heat computations. It's just that when there's a phase change, you have to use different constants. So there is a heat of fusion and heat of vaporization. Okay, I think you've seen your tables or your for the data tables. For heat of fusion, we see that as delta HF, and for heat of vaporization, we see that as delta HV. Okay, so let's just go to this little diagram here. So when it's solid to liquid, fusion happens in this area. Okay, so when the solid becomes liquid and vice versa, melting, when of course you know that very well, in the liquid to solid, when it freezes, this is where your delta HF happens. And of course, for here, this portion here, this is where HV happens, or vaporization. So, of course, when there are phase changes, you can see from the diagram, it talks about enthalpy. It doesn't talk about specific heat when there is a phase change involved. I want to stress that. I wanted to take note of that. When there's phase changes involved, or there are phase changes involved, it's enthalpy. And when it's just the heat of a system or an object, it's just your usual MC delta T computation. Okay. So before we move further, I just wanted to take note of endothermic versus exothermic. In one of your lab activities, we'll be understanding this further. But for now, I just want you to take note of what the difference is. One is endo. It's not the endo, like end of contract. It's different. It's just endothermic, and the other one is exothermic. When you say endothermic, heat is taken in by the reactants, or there is an increase in temperature. So you can see here from the definition, Q is positive, it's endothermic. Q increases, which means heat increases, there is an increase in temperature. For exothermic, heat is released as a product. So your system releases heat. So when a system releases heat, it means it cools down because it transfers its heat to the other system or the other object. And you can see here that Q is negative or less than zero, meaning there is a cooling down process. So that is an exothermic. I hope you don't interchange the two. Endothermic, Q is positive. For exothermic, Q is negative. It doesn't mean Q is negative, it's below zero. It's just, it's cooling down, okay? Okay, I hope that's clear. So now let's go to the example. So I was really stressing from the PowerPoint that enthalpy is very useful when the system is uh, using phase changes. Wherein, for example, ice to steam, like in my example. My example talks about the conversion of 200 grams of 25 degrees, negative 25 degrees of ice to 150 degrees Celsius of steam. So I'm giving you a set of data when a problem like this is given. So let's just be clear. What's a heat problem, a specific heat problem, or a calorimetry problem is given to you? We will be, of course, responsible in giving you the data. Now, there could be changes or there could be differences with regards to the decimal points that you are seeing. I understand that, of course, your guides are online and you can research the different values. So instead of giving me different answers because of the data that you gathered also comes from different sources, what I want you to do is to use the data that I'm going to give for the specific problem set or for the specific problem. For example, here in this problem, I'm giving you specific values for the different concepts that we will be using. Please use them. Like in our previous example, I kept on getting messages, ma'am, what is the specific heat of copper? I see that it's 0.384. There's one that is 0.386, one is 1.385, and then I said, please use 0.386. So please rely on the value that I give so that when I'm checking your work, most of your answers will be similar or the same. It's because even if that little difference in the decimal point or the decimal place might give different answers, and at one glance I might uh, mark your work incorrect because of a slight difference, but I will of course always rely on the solution that you're giving me. But I hope now in this video you are clear that whatever data specs or data sheet that I'm going to give, you'll be using that data. So in this example, we're trying to convert. Okay, let's get the given. Aside from this data, we have given here from the problem. Okay, mass of ice is 200 grams. Okay, so the initial temperature of ice is -25, and the final temperature that we're trying to get is 150 degrees of steam. So, of course, you know very well that ice doesn't go straight to steam. Have you seen ice that becomes paper right away? No. So, you really have to understand what to do in this problem. So, I have here a blank sheet. So, that's ice to steam. So, I just want to lay out to you what you really need to analyze. So for ice to steam to happen, this is -25 degrees Celsius of ice to 150 degrees Celsius of steam. So first step, you have to analyze ice at -25 becomes ice at -0. Or at zero or negative. Why did I even put negative? I'm sorry, let's remove that negative. Wait, let's see that. I hope I can delete that. It doesn't get deleted. So instead, I'm going to use my pen tool. I have an eraser. There you go. Why did I even do that? So ice at 0 degrees. Okay. So let's get my pointer again. Next step. Once it's still ice. So this is what you call here, there's a change in temperature but not a change in phase because it's still ice. Okay, that's the first step. Second step, your ice at 0 becomes what? It becomes water, right? At 0. I hope that's clear. Okay, let's go back again. Ice at -25 is still ice at 0. Why is 0? Why is 0 our reference point? 0 is the freezing point of ice. Okay, let's complete this so that when you get a snapshot of it, it's actually more detailed. Okay, and they're still new to this writing tablet thing. Needs practice. I actually need practice. Okay, let me do my eraser here. Here it is. And okay. Okay, there you go. Now, third step, it's water. It's water at 0 degrees. So let's take that as water at 0 degrees becomes what? It becomes water at 100 degrees Celsius, right? I hope you get what I hope you can imagine what I'm getting at. You have to boil it. For it to become steam, it needs to go to a certain temperature and then you have to boil it. Okay. But it's still water. It's still water from this temp to that temp. Okay. Fourth stage. It's water at 100 degrees Celsius. Now it becomes what? Once it reaches its boiling point, it becomes actually steam at 100 degrees Celsius. Well, I hope you get that. And finally, we're almost there. So the fifth step is actually steam at 100 degrees Celsius to steam at 150 degrees Celsius. Okay, I'll go back to this step. If you go back to the problem, oops, really, there you go. I was actually surprised it did that. It says here you just need to convert 200 grams of negative 25 degrees of ice into 150 degrees of steam. So trying to convert ice to steam. But of course, ice can just become steam in one step. So you have to really understand the phase changes. And then it says there how much heat. Sometimes the problem would say how much energy. Okay, but it's all the same. I just want you to get the process on how to analyze a problem like this. So we go to the solution or part of the solution. It says ice to steam. That's the first step. It's ice at negative 25 and then it becomes ice at 0. And then second step, it's ice at 0 and then water at 0. Of course, it melts. Here, it has to go up a certain temperature because you have to make it melt so that it becomes water and later on it becomes steam. And then water at 0 becomes water at 100. Why is this step important? Of course, you have to boil it. And you know that the boiling point is actually 100 degrees Celsius. And then water at 100 to steam at 100. So water to steam. And finally, steam at 100 and steam at 150. For enthalpy, you just use the formula. Of course, H is actually M delta HF, or H is equal to M delta HV, right? So, but you can check. I said when there are phase changes. So where are the phase changes happening? This one, and I believe this one. Okay. So there are two parts in this 5-part solution wherein we'll be using this formula HF and HV. But for this is 25, 0, 0 to 100, 100 to 150. These are classic H or is equal, I'm sorry, Q equals MC delta T. Okay, I hope that's clear. And then this is also an MC delta T step, and this is also an MC delta T step. And to get the total heat of this system, all you have to do is add Q1, Q2, Q3, Q4, and Q5. Okay, I hope you're getting that. So, not sure. Wait, let's keep them. Let me add a new slide here so that we can continue with the solution. Okay, there you go. So what is Q1? Okay, let me get my pen tool again. Okay, Q1 will be, let's do it here. Q1 is, I said, if we go back, Q1 is an MC delta T. So that's MC delta T. The mass is 200 grams. And then here, water is what? Water is in an ice form. So we will be using the specific heat of ice, which is 2.06. Okay, and then for delta T, okay, what is the initial temperature? It's when you say delta T, it's always final minus initial. So what is the final temperature? It's 0 minus, right? And the initial temperature is negative 25. Let's change that grouping symbol. So that's 200 times 2.06. I think I have a calculator somewhere here. Let's see. Okay, if you are having questions for this video, please jot them down and we can do them and ask them over chat or over our face-to-face class or our synchronous class. 200 times 2.06 and then times 25. So that's I'm getting 10,300 joules. Okay, that's Q1. Okay, that's 1. Pardon my handwriting, I'm still getting the hang of it. Okay, I hope you don't mind if I'm gonna refer to I have a cheat sheet for the values, not really the solution. I really haven't solved this before. So just for me not to go back to the slides all the time. Okay, the next one is Q2. Okay, for Q2, it's a phase change part. Okay, this is Q2, it's phase change. So let's have that. Q2 is actually ice to water. So it's M delta HF. We said that solid to liquid, it's using fusion. So the mass is 200 grams times delta HF, or the heat of fusion of water. So it's 334. So let's use 3. I'm sorry, I was typing 8. 334. So this is, let's compute that again. That's 200 times 334. That's 6. Okay. Okay. 66,800. I'm getting that. Okay, that's Q2. Okay. Now let's get to Q3. That's water at 0 and water at 100 degrees Celsius. So let's have that. Q3 now is again an MC delta T. But here, if you can check, we said that it's already water. So we'll be using the specific heat of water. So mass is 200. And for our given, the specific heat of water is, it's 4.19 times delta T. What's the initial temperature? The initial temperature is, you can see here, it's 0. And the final temperature is 100. So that's 100 minus 0. So that's 100 here. So our value, yes, believe it or not, I'm just solving this problem today. So 4.19 times 100. So that's 8,800. Okay, joules. And then it's for Q3. Okay, I hope you can still see that. There you go. And then for Q4, going back, Q4 is water to steam. So that's heat of vaporization. So that is equal to M delta HV. So the mass is 200 times the heat of vaporization of water. We're given in this problem 2257. So that's 2257. So that's just 200 times 2257. That's 451, 400. So that's 451, 400. And finally, Q5. So Q5 is what? Q5 is a change in temperature. That's MC delta T. So 200 times the specific heat of steam. It's 2.03. And then it's 150 minus 100. That's 50. So our final answer here is 200 times 2.03 times 50. That's 2,300 joules. Okay. So what do you do? How do you get the total heat of the system? All you have to do is add them all up together. So, okay, where can I put QT? Okay, let's just put it here. QT now is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. Okay, but first, of course, it's very important that you double check your values. But I'm assuming that we got the correct value since they seem to be correct. Okay, so let's add them all up together. So I pardon my handwriting, it gets better through time. So that's 10,3 plus 66,800 plus 83,800 plus 451, 400 plus 2,300, and that's 632,000. I'm getting QT as, okay, why not, let's just use another slide. Okay, let's keep that so as not to like, that's a very call this cramp up. So let's have it here again. Just get my pen tool. Wait, let's see first. Shift F5. I'm sorry. Cute. Okay, let's get my pen tool. Okay, let's be clear. So for our for our final or total Q, that's Q1 plus Q2 plus Q3 plus Q4 plus Q5. Just add them all up together and we got what? Okay, let me just review my computations in my calculator so that when you're trying to review for this problem, so we're getting, okay, it's 10,300 plus 66,800 plus 83, 83,800 plus 451, 400. Okay, 451, 400, and finally for Q5, that's a 20,300, and our QT is equal to 632,600 joules, or this is equal to 632 kilojoules. I hope that's clear. Okay, again, if I want to go back to that process, ice to steam would involve 5 stages. Okay, you have to identify the phase change part and the temperature change part. And there's a phase change part. That's where you use your delta HV or delta HF. When there's just changes in the temperature in the object or in the system, all you have to do is use your basic mc delta t equation. Okay, so hopefully this short video on enthalpy will help you in solving those enthalpy related questions in your, excuse me, thermochemistry module. And I will also be uploading more. I hope you always check this channel for more videos for your chem class. Okay, for now that's it. Again, you can share this video to your other classmates or other friends taking up chemistry. And should there be questions regarding the solutions or the concepts that were presented, please don't forget, just you can PM me in FB or use our group chat or use that big blue button in Canvas. Okay, till our next video. Okay, bye bye.